All right, today we'll be doing variational autoencoders for the second part of the recitation, and for the first part you will be doing representation learning. So what is representation learning? Designing the right set of features for a particular task automatically, as opposed to manual feature engineering in traditional machine learning approaches, is called representation learning. So whenever you try stuff like SVMs or logistic regression, you tend to find the right set of features in order to understand what is necessary for you to build a model and make the right predictions. But in deep learning, this is probably the paradigm shift in deep learning, that it does the representation learning also for you, even if you give it some naive representations. So the main focus in deep learning is that we merge the representation and classification into a single unique task, and we assume that the neurons learn representations as well. So most of the times we keep getting questions on Piazza, or whenever your homework part 2s have been released, that what is the right architecture that we must be using, how many hidden neurons should we have, how many layers should we have, and all of this. We should tell you that there is no right answer to this, because all of it depends on a lot of experimentation. But what you can say for sure is that you have to consider two things when you're trying to build your models. One is that one is the optimization aspect of it, where you can say, can my model learn by stochastic gradient descent or gradient descent or any such kind of paradigm and generalize well. You should understand that if you're increasing the depth, why are you doing so, and will skip connections help? Like in ResNet, skip connections helped for your second homework. And if I add a dropout, will it help me or not, or batch norm and all of these. And when you're thinking of all of these, it's important to think what these functions do for you. If you're having very little data and you try dropout, then you're probably not headed in the right direction, because sorry, if you have a lot of data and you're doing dropout, you're not headed in the right direction, because dropout is always done in order to reduce the amount of overfitting. So if you understand the math, or at least the intuition that is there behind all these functions, it's very useful for you to build your networks. And then another thing that you should think is about the kind of representations that you're using. So if the kinds of representations that you're using can capture the inner structure of your data and what is the kind of task that you're working on, if these networks can give you answers to the task that you're working on. And also you should understand the fact that optimization and representation are complementary as well as supplementary, which means that sometimes they help each other and sometimes you need to balance out. And when you're trying to work on different tasks, also think why some networks might be more important than the others. For instance, when we do a lot of image classification, we look at CNNs, and the major reason behind this is because they tend to be translation invariant, and you want to be able to find a particular object or detect something no matter where it is. And Professor Bhiksha covered how CNNs are translation invariant. And when we're doing a set of language tasks, we generally tend to use RNNs because they have long-term dependencies. That is, you need to look at the entire sentence before you can generate something, etc. And why do we use attention in sequence-to-sequence models? If you've already started sequence-to-sequence, then you'd probably know. But if you have not, generally attention is used in sequence. So when you start using sequence-to-sequence, which is a part of your homework for part 2, you will realize that attention will come very handy, because a decoded words representation should be correlated to some specific input words. If any of you have gone back and seen attention, it generally means that every decoder time step can look at some particular words in the encoder and focus especially on them instead of looking at the whole chunk. And so the main thing that we would recommend is that rather than focusing on tricks or academic recipes, think of what design makes sense with the properties you seek in your representation and the kind of task you're doing. This is also useful for your project, because we have seen a lot of students come up and say that there is this project that we want to try, and we just want to try and use GANs. But before using fancy architectures, it's very important that you think if it works for your task and if it makes sense to use that architecture for your task. And always we would suggest to start simple and then increase the complexity of your architectures. For instance, think of something like sentiment analysis. I mean, if you intuitively think of it, it makes more sense to use CNNs in sentiment analysis than RNNs, because in sentiment analysis you're just looking for some particular words that give you a signal that this is a positive or a negative sentiment. You're not looking at the long term dependencies. So CNNs make more sense than RNNs. So generally, when people learn representations, there can be different ways of doing so. The very first thing is end-to-end, what you usually do, otherwise in assignments, etc., when you train your entire model for a particular task. You can also do it in an unsupervised fashion. We'll be also covering autoencoders today. Another very new kind of task where people tend to do is that you train it on an alternate task and then come back and test it or fine-tune it for your task. This is exactly what you did in homework 2 part 2, where you trained it for a classification task and you you fine-tune this model, or you just use the representation for the verification task. And another thing that you can totally do is use like a pre-trained model. If you guys have heard of Word2Vec or FastText or even BERT these days, they are all pre-trained models that is trained on a huge amount of data. And you can directly use these word embeddings for any task that you want. So if you use a representation learned one way and move on to a task you're really interested in, you can either fine-tune the representation or fix it and add deeper layers. So what generally people tend to do is when they're using BERT, they want to either fix the embeddings that they get from BERT, or even backpropagate the gradients to the BERT network. It's totally dependent on the kind of task and the amount of data you have. If you have very less data, it doesn't make sense to fine-tune BERT or any other large network like that, because the amount of data you have will probably not change the network too much. So yeah, again, think about what makes sense based on the data you have and the task you're interested in, and don't just go with fancy things or just huge networks. They might not always work. And we'll now go through some examples for different kinds of tasks. So transfer learning is basically one paradigm that people use when we have less data and we have the same domain data, but we do not have the data required for a particular task. Then what we do is we train a neural network on a very easy to train task, and then we change the final layer and fine-tune it on the harder task where you have lesser data, exactly like you did in homework 2 part 2, but people do it in a very large scale. So there can, some examples of this kind of transfer learning is, one is that of semi-supervised learning, where you train both an unsupervised model and the supervised one with or without shared parameters. A very simple example for this would be, consider translating English to French, and you have a lot of text in French and a lot of text in English, but these are not aligned together. So when you have to train a translation model, you need to have parallel corpora, which means that you need to have a sentence in English and a corresponding sentence in French. But what do you do when you do not have data like that? So one approach that people generally do is you train the encoder as a language model in English and train the decoder as a language model in French, and then finally just plug them together and train the attention weights on the translation task. Obviously, this is not as good as a sequence-to-sequence model with parallel corpora, but obviously, I mean, it will definitely learn something better than training separate models. So here, what you're trying to do is you're training your encoder completely to understand English data and the decoder completely to generate French data, and you're learning the attention weights for the sequence-to-sequence model. So now we'll come to the concept of unimodal representations. So we'll go over some modalities like text, audio, or images, and understand how we can use pre-trained networks for these different modalities. And in case of image, generally people tend to use ImageNet, because ImageNet is a huge data set and it is almost considered to be solved these days with the new networks that have been coming up. And you can also find pre-trained models that are trained on ImageNet in your Torch Vision package. So if you want to train a domain-specific classifier, consider loading the pre-training model and then fine-tuning on your data set. There are some teams that are working on visual question answering or something to do with captioning and things like that. You can totally use networks that are trained on ImageNet and transfer it to your task. And then, if you want to train another general task, for example, a visual question answering task, you can simply encode all the data set with the pre-trained model at once, then learn a network that takes the representation as input, which is exactly what I was saying. So you should also make sure that when you're using these pre-trained models, you use the image specifications that they had given you. Like, for instance, assume that the model was trained on RGB data and you use black images, obviously it will not work. So you should go through the specifications, the documentation properly, and make sure that your image input is similar to what input was given during training. For projects or assignments that involve text, people use word embeddings, which are word-level representations that are trained on some particular objective. Most of you must be familiar with word embeddings like word2vec or glove, which are static embeddings, and you can just use the weight representations from these word embeddings as the representation when you're transferring it to some classification or generation task. They are also, these days, the good thing is that we have contextual word embeddings like BERT. What is the difference between a static word embedding and a contextual word embedding is that when you, in a static word embedding, for a given word, you always have the same weight representation or the same weights. In a contextual word embedding, it depends on the sentence. For instance, I mean, this is a very stupid example, but consider something like someone saying, I love Apple. It could be Apple the company or Apple the fruit. And depending on what the person has spoken until now, I can probably distinguish between both of them. And when I'm using a word2vec embedding, it would give me the same embedding for the word Apple. But when I'm using a BERT contextual embedding, it would give me two different embeddings depending on the context of what the user has spoken until now. So it's very useful to use BERT embeddings, but this also comes at a cost that BERT is sort of heavy. Even if you use the pre-trained models, it is sort of heavy because you're basically running an entire transformer model before getting the embeddings. So again, you have to decide if you can afford to use these embeddings, and if you're using it for a task, do you want to fine-tune it, or do you want to freeze the BERT layer, etc. And for audio, there is this pre-trained sound encoder, which is trained with audio frames, which is called VGG-ish. You should definitely go and check it out if you're working on audio data. And generally, what people do for video data is that they use networks that have been trained for images, but I mean, they obtain the image frames that are sampled from video and then use this in order to train their video networks. You could also, I mean, generally what people do is they sample it and use the sequence of images, or just obtain the mean and get one image representation and use it. It again depends on the kind of task you're working on. The next kind of representations we'll be looking at are multimodal representations. What I previously explained is that we have just one modality, that is either text or audio or speech or video. But there would be some tasks where you would have to merge two different modalities and learn from both of them. Example, visual question answering, where you're probably given a question, you're given an image, and you have to give an answer. So you're getting input in terms of text as well as image, and you have to get signals from both these representations. One approach that people follow, one very naive approach, would be to simply concatenate representations and plug them to your end-to-end task. If you look at this image, they have some representation from the audio, they have some representation from the video. Just concatenate both these vectors and get like a shared representation and pass it probably through a linear layer or something like that for your classification task, or depending on what your task is. So the good part about this, is extremely easy to implement. You're just taking two different modalities and concatenating them. But the downside to this is that it does not capture interactions between modalities. So assume that you were doing a VQA task, you're just getting image features and you're just getting text features. You're not understanding which part of the text is correlated to which part of the image. And depending on the question I ask, you might have to look at different parts of the image. So it sort of makes sense to understand what are the relations between these two modalities instead of just taking two representations and concatenating them in the end. So what can we do about it? Another approach that we look into is bilinear pooling, where we use an outer product on the unimodal representations. So assume that you had an audio representation and say a text representation. You basically obtain the outer product of both of them. You just a dot product of the entire thing. So the pros of this particular representation is that it captures every pattern, because you're just taking every element and multiplying with every other element in the other modality. And it is very good for complementary modalities, because if you want to look at the relationships between these modalities, it sort of captures that. And when they contain like different kind of information, all of that is captured. And what is the con of this is that you will obtain lot more richer context or data than is required, and sometimes it can be redundant. Like I told you, you're getting like an outer product of the two vectors that you have, and you're computing the product of one with every other element. Sometimes it's redundant and not necessary. And it also becomes untrackable sometimes. But there are new methods like compact bilinear pooling and tensor fusion, which you should definitely go and look up if you're looking into bilinear pooling or using two different modalities. And the last thing that is sort of smart, a very smart thing to do is to use autoencoders. What autoencoders generally do is they encode modalities in a shared space, and they're trained in an unsupervised manner, being that in autoencoders your input is X. Say your input is X, your output is also X. That is, you do not require labels because you're trying to encode your input into some compact format, and again deconstruct that format from the encoding that you have. And later what we do is, once we have trained this entire network, that is, you give an input, you get some representation, and you get you reconstruct that input from the representation. You basically remove the decoder part of it. So what the encoder contains is a very well-trained network in order to understand representations and put them into a compact format. So that is about autoencoders and how they can be useful for different downstream tasks. You can train autoencoders and remove the decoder part and use them for different tasks that you require. The pros is that autoencoders are extremely robust and they can reconstruct missing modalities. There have been a lot of really cool experimentations with autoencoders where if you cut out some parts, one thing that I can remember of is that people train it on images and audio. So when you can see someone's lip movements, you can basically understand what they were talking back in the audio. So that is one really cool application of autoencoders. But the cons is that you will need separate data training, and often it's not very good as compared to pooled or coordinated representations, which are much more sophisticated ways of representing data, which you again should go back and look up if you're really interested. Now Ethan will cover variational autoencoders.
Hi everyone, so we started to talk about variational autoencoder. So this is a totally different direction, and we just talked about representation learning, in which want to basically map the input to a hidden code or a hidden representation, a latent representation. But for variational autoencoder, our target is essentially you want to generate something out of a latent code, and we want to study how we could achieve that. So we still want to start from the autoencoder, so we've talked about that. So basically we have an encoder, we have a decoder, we have a reconstruction loss to penalize the difference between the reconstructed sample and the original sample, x prime x. And we already talked about this, that we could use autoencoder for representation learning. So we could consider x being the text, so we can have z for the text embedding, the sentence embedding, or the word embeddings. And also we could have x for the image, and we reconstruct the image, and we have the latent image embedding. And so nice thing is that it's totally unsupervised. We have a ton of unsupervised data. So basically, we could have unsupervised learning to train a lot of meaningful latent embeddings for these information. So, but consider this. So for the autoencoder, basically we want to use the encoder. We want to use the encoder part. But what if, so we just train a good enough decoder, so we just throw it to the trash bin? Or we could figure out something we could do with the decoder. So one thing we consider here, actually, let's just take this decoder apart and say, somehow we could throw into some z's, some random z's out of nowhere into the decoder. So what could we get out of the decoder? So you can see that actually we could actually expect the decoder to be a pretty good generator of some data. So this is great because by this way, essentially we're creating the world out of nowhere. Like so we managed to know some kind of truth, actually some kind of something that actually generated the world. But one thing is that where are we going to find these z's, these random latent vectors, or these latent representations, these latent embeddings? So you can see that essentially in the autoencoder setting, we don't have any constraint, or we don't have any distribution, or we don't have any knowledge of these z's. We just there's some kind of latent product generated in between, but we have no idea where they are. So let's consider this. Say if we could somehow plot this z, so this is just a two-dimensional z, and say what if we just pick those z's from this plotted latent space, and consider that we have these training data sample here, and we just want to do an interpolation and to try to get some kind of z, and we could generate something out of it. But you can see actually we don't have any constraint for this latent space. So this latent space is not even necessarily continuous. You can see that there could be lots of gaps here, and if we happen to interpolate something, say this point here, actually for 7, and this point here for 1, and we pick the point in between, we basically we just get trash out of this point for this z. And also because we don't have any distribution assumption for the latent space, so it totally makes no sense that we could do it this way. So variational autoencoders basically improve this by, let's just model the latent distribution. Instead of in autoencoder, we're modeling a deterministic sample, a deterministic latent representation. But in VAE, essentially we model the latent distribution rather than a deterministic sample. So let's change the encoder, say, now the encoder actually gives a distribution over z. So you can see that x here, and we consider we have a q of z given x out of the encoder. So yeah, in practice, we just model the parameters of this distribution. But you could see that still we could have arbitrarily q of z given x of this distribution. It could actually distribute it anywhere in this space for this z, in the, say, consider a d-dimensional random vector. So how could we sample the z's without conditioning on some x, saying that we want to generate some kind of x here out of the decoder, and basically we cannot generate an x out of some q of z given x because we don't want to condition on this x. So it's easy. We just consider prior for the z. Say, let's consider in the real world, these x samples are actually generated from this decoder from some prior distribution for this given z. And what if we just want to train the encoder to reflect such a prior distribution? We could just, so apart from this reconstruction loss we have for the autoencoder, we just add a KL divergence loss for this prior of z and every posterior of this q of z given x. So this sounds simple enough. So basically, this is what we have for our autoencoder. We want to have the autoencoder story. We want to somehow compact or squeeze this x to a latent representation, and we want to reconstruct an x out of this latent representation. And also, we might want to have some distribution constraint or some, we want to regularize this latent distribution for this latent representation. So we could have, so now we have the prior for the z, so we could just draw a sample from this prior, and we could generate some x. So the story here actually seems simple enough. So we can actually look at some training result for this one. You could see that after such a regularization for the latent space, we could have those z's distributed pretty decent. They distributed continuously and smoothly in the latent space. And actually you could see that those x sample from these z samples in this two-dimensional latent space, they have some continuity out of this sample. You can see that actually have the 1 here, and it gradually changed to 7 or 9 or something. We have 4 here. So we have a pretty decent continuous latent space. Okay, so this is just some kind of intuition that actually we just, it seems that we made some simple enough change to autoencoder, and we just get this result. But one amazing thing about variational autoencoder actually, if I have a very sound probabilistic or mathematical background, that actually made this story very perfect. So let's consider this. From a probabilistic theory point of view, what is the variational? So variational is just some fancy word for doing, we have variational method for functional analysis that basically want to do optimization on the function space. But essentially, actually, we have parameters for the function. So in this scenario, it basically boils down to an optimization also on the parameter space. So for this interpretation, we want to look at the generative process in the decoder part. Say, in reality, we do have such a generative story. Say we have a prior for the z, for this latent representation, or this latent code, and we generated these real samples from from some kind of oracle distribution, p of x given z, out of this z. So now, essentially what the decoder does, actually, we're interested in the inference of the z given an x. So in decoder, we generated, say, we have a real-world decoder, and we can actually generate some x out of this z. But now we're interested in how can we use it encoder to infer this z back given this x. So we can see that actually, if we want to solve this directly, we want to look at how can we work out p of z given x. This is intractable actually, because look at the denominator. You have an integral here, and you want to do an integral over all the possible z's. So basically you see that over some d-dimensional space for that z, basically this is intractable. So a common technique for dealing with such inference, actually, we have a probabilistic graphical model. We have the variational inference that we can actually introduce a variational distribution. So here means that it's a distribution, it's a variational distribution. So want to do the optimization on this specific distribution, on this specific function, and eventually we could have a very good variational distribution of q of z given x parameterized by theta, and it could give us some good approximation of this p of z given x itself. So so common things that we want to make them close by minimizing the KLD of this q, this variational distribution q theta, and also the true p here. It is somewhere, but we just cannot calculate it. So so good. How could we approach this? So let's first rewrite a KLD here. So it would actually we could rewrite it to a some log of the marginal of x and minus a elbow here. So what is the elbow here? It's actually an evidence lower bound. So you can see that actually the KLD in the left-hand side is basically greater than or equal to 0. And when it's 0, it's great. So when this KLD is 0 here, we actually have a q theta, the variational distribution, exactly equal to this p here. So we can see that because this one's always greater than or equal to 0, we would have this one being a lower bound of the marginal of x here. So instead of, we want to minimize this KLD here, so essentially we could just maximize this elbow here. So if we do some mathematical magics here. So if we work it out, actually it is equivalent to the log of p of x given z over these z samples from the posterior distribution of z given x, and also minus the KLD of this posterior distribution of q of z given x, and the p, the prior of z itself. So we could see that one amazing thing here, actually, this is exactly correspond to this loss we consider here. So we have x here. So this encoder give us a q of z given x, and then we basically will sample z from this q of z given x, and then we want to reconstruct x here. So consider there is a p of x given z here. So for the reconstruction loss, essentially we want to consider for the original sample, we want to see its likelihood in this reconstructed distribution of p of x given z. And also the second term is exactly what we'd have for the KLD here. So we can see actually we have a very good mathematical story for not just how we approach VAE out of some intuition from the AE, some limitation of AE, but we're adding something. We want to constrain the latent space, and eventually we just get VAE. But also it has some very decent mathematical interpretation or probabilistic interpretation for actually explaining how we actually get to this point. So it's actually out of a very common variational inference techniques we have for doing such an intractable inference. So so basically this is it for the theory part of VAE. So in practice, how we could do this, so we still need to do this in deep learning. So you can see that we have two parts for the loss function. One is the KLD. So simplest case, we just consider, say, we have some r to the d vector z, and also the prior just being a simple enough a normal distribution. And also we consider we're going to model this q of z given x being a Gaussian of some mu and sigma generated, some mu and sigma parameterized by this theta, and it's given by how we're passing the x, and we just get this mu and sigma. So actually the KLD here boils down to a very simple form. So it's just this one. And if we further consider isotropic covariance matrix, it even gets simpler, because you can see that actually this trace here and the determinant here actually could be factorized if we consider a isotropic, a spherical covariance matrix. And also another thing is that how we could train this with this reconstruction loss. You can see it's actually a expectation form. So normal thing, that common techniques we want to do with this expectation is we want to do sampling. That if we draw enough sample and we take the average, take the mean, so basically we're approximating that expectation. So so it's easy enough that we just draw sample out of this cube theta of z given x, and we do the mean of these k samples. And another thing that you could see that actually we have from the encoder we have this mu and sigma, and we try to draw sample out of this Gaussian parameterized by this mu and sigma, and we want to train the decoder. But you can see that we actually break the backprop chain here. We have a sample step. Basically, we cannot backprop through the sampling step. So one thing here, actually, we want to do the reparameterization trick. Is actually if we just sample some epsilon I in advance from a normal, and then we do this transformation. So basically, we have the zi this way correspond to a sample from this q theta here. So we have a so actually we're essentially doing the sample of zi as if it was sampled from this Gaussian distribution. So now we have this continuous computational chain, so you could do the backprop. So it's quite similar what you have for the gumbo trick for sampling out of a categorical distribution. So we could see some results here. So one thing is actually we could have some very decent continuous latent space. If you somehow plot these phases in the latent space and do an interpolation, so you can see that we could see these phases changes, how these phases change continuously from one point to another point. So, so we have the paper, we have a reference here. Another example with text. So this is essentially using a VAE for a language model. So we have two latent representation for two sentences here. And let's try to do an interpolation from these 2 points of the latent representation for these two sentences. And we can see that in standard encoder decoder, those intermediate results seems they're not making a lot of sense, we could say here. But when it comes to VAE, it's actually better. So you could say this, I want to talk to you. So gradually changes to, she didn't want to talk. She didn't want to be with him. So I want to be with you, and I don't want to be with you, and I don't want to be with you, and she didn't want to be with you. Him, actually. So he was silent here, so for a moment, it's quiet for a moment, dark and cold, and something, and gradually changed. It was my turn. So this is several examples they give in this paper. So yeah, so basically this is what we cover from those. So from two perspectives. So how could we gradually come to VAE from the intuition of how we want to do a better latent space and do a better generation, and also we have those interpretation from a PGM point of view, say probabilistic graphical model point of view, and how we're gonna approach VAE. So we're not providing code here, so you could check this tutorial. So I can actually click on the link here. So basically, it's you have some tutorials in PyTorch examples, so you could take a look. So because we're not covering this one in homeworks, so you could take a look, and you'll find this one very interesting if you want to work on such a topic for the final project. And also, I think next we want to cover GAN, and there could be a different kind of a generative model, but there could be a unified interpretation or unified story for GAN, for both GAN and VAE. And we also have some other more advanced variations, such as adversarial AE, or something called adversarially regularized autoencoder or something. So based on a combination of those adversarial training and adversarial part out of a GAN and also VAE, and you can actually, all of these will correspond to something. We have a probabilistic interpretation for all these variations, starting from VAE and GAN. So, so I wish you could have a better view of these generic models from this one and after next week's recitation about GAN. So yeah, so thank you. So we might still have time for questions. So